Last time we were talking about the multiplicity of an ideal gas of anything from 1, 2, up to n molecules. I want to continue along those lines, and I want to do it in conjunction with defining a very, very important quantity in physics called entropy. So, from what we've seen so far, is that the tendency of a system is that it will arrange itself, whether it's by energy, volume, number of particles, whatever the case may be, such that the multiplicity is maximized. This works for large systems. You can't prove it, but that always seems to be the case. But we're going to make the following bold claim, and we're going to say any large system in equilibrium will be found in the macro state with the greatest multiplicity. It's a bold statement, but it's even more difficult to try to disprove. In a sense, this is a general, probably one of the most general statements of the second law of thermodynamics. Multiplicity tends to increase. Now, for those who've studied some thermodynamics earlier, you probably saw one definition of the second law, or one expression of the second law, as the entropy of a system tends to increase. And now what we want to do is relate the quantity of entropy to multiplicity. And we do it in this way. Because multiplicities are enormous and unwieldy, we prefer to work with entropy because we write entropy as k times the log of omega, where k is Boltzmann's constant and is equal to 1.38 times 10 to the minus 23 joules per Kelvin. So this is a fundamental, in fact, it's so fundamental that an expression similar to this is inscribed on Boltzmann's grave. Let's see how this applies to what we've done already. Let's look at remind ourselves of the Einstein solid. Remember, we found that doing the approximations we needed to do, where Q is much, much greater than N, we found that we could express the number of accessible states as EQ over N to the nth power. Therefore, the entropy in that case I could write as SK log of EQ over N to the nth power, which I can then write as K times the log, I can write as NK times the log of Q over N plus 1. So if, let's say that N was 10 to the 22 molecules, and let's say Q was equal to 10 to the 24, we would find that the entropy for that particular configuration would be something like 0.77 joules per Kelvin. And of course, if either N or Q increases, so will the entropy. In fact, so in the case of an ideal gas, we can think of increasing the entropy either by increasing the energy or the number of particles, or increase in the volume of the system, or I could mix two systems together. In general, entropy for gases greater than entropy for liquids, greater than entropy for solids. Solids are the most orderly of the three types of matter, and this is generally true. Also, if I have a combined system, generally speaking, if I add the entropies of each system, that will give me the total entropy of the combined system, so we call that an extensive quantity. Entropy is an extensive quantity. Now, of course, that stands to reason because we know that multiplicities multiply one another, so the log of a multiplicity would be adding one to the other, so entropy should add the way multiplicities multiply. So let's look at the entropy for an ideal gas. So I can go back to that previously hideous expression for the multiplicity of the ideal gas. Like such. I take the log, so S is equal to K log omega sub n, and that's going to give me nk times the log of v over n, 4 pi mu 3 n h bar squared to the 3/2 plus 5/2. This is what we call the Sacker tetrode equation for computing the entropy of an ideal gas. So this is a much simpler form of, much simpler expression, entropy, than multiplicity. But this is good for an ideal gas. Notice the way this is written, good thing, if I increase the number of molecules, I'm going to increase the entropy by the same factor. That's good. And this expression will work. I want to look at some interesting cases, though, of the ideal gas. Make things a little bit more complicated. Suppose I do the following. Let's look at a mixing situation. Suppose I have two systems of gases, but they're different. Suppose I've got, maybe one is helium, one is argon. Some way, so I can tell the difference between a helium atom and an argon atom. So let's say I've got molecules occupying each side of the container. I divide the container in half by a partition. Each one has an energy and number of particles and so on and so forth. But now I remove the partition. Let's see how the entropy increases. So for gas A, I could write the change in entropy of that gas as nk log of the final over the initial, or nk log of 2. And of course, the same thing would work for the change in entropy of gas B. Same deal. And therefore, the total change in entropy, additive, should be 2nk log of 2. Okay. On the other hand, so these are different gases. On the other hand, suppose the gases are the same. So I got the same exact configuration, but instead of having helium and argon, I have helium and helium. Well, if that's the case, delta S is equal to 0. Interesting. Take a slightly different approach. Let's start with 1 mole of helium in a container. Entropy associated with that is going to be equal to NK log of N 4 pi mu 3n h bar squared 3/2 plus 5/2. That's Sacker's tetrode equation. Now I'm going to add 1 mole of argon to this. What I expect is that the entropies going to double, roughly. You know, they're not exactly the same entropies, but the mass of argon is greater than the mass of helium. But so for all intents and purposes, it roughly doubles. But notice, in that equation, if I double both V and N, or I should say N and U, you don't double the entropy. If I look at each term, notice that I'm not getting double, I'm getting a factor of 2nk log 2 less than double. So I'm less than double, even though I know I should be double, by the factor 2nk log 2. This tells me that this factor, to add back in, must be due to the entropy of mixing the gases together. So there's an entropy associated with each gas, but there's also this other entropy that I associate with the fact that I've mixed the 2 gases together. And by mixing the gases together, I've essentially increased the multiplicity. Now, we had that n in there, that n factorial, to ensure that we took care of the distinguishability between the 2 gases. Remember we said if the gases were indistinguishable, we have to divide by a factor of n factorial. If we had not put in that factor of n factorial, we would have had an equation that looked roughly different. It would have looked like this. Without that factor of n factorial, it would have been S equals nk log V times 4 pi mu over 3n h bar squared 3/2 plus 3/2. This would be for distinguishable molecules. But this is wrong. This can't be right. And here's why. Suppose this were correct. Let's say I have this ginormous volume of helium gas. Notice what would happen. Suppose I insert a partition into the tank of helium gas. Divide it in half. This equation predicts that each half would have much less entropy than the combined system. In other words, by inserting a partition, I can actually decrease the entropy of the system according to this equation. Well, that's a violation of the second law of thermodynamics. And of course, it doesn't happen. So that's why it's so important that when we have distinguishable particles, that we insert the factor of 1 over n factorial so that we don't overcount the number of molecules or possibilities and account for the fact that a gas of all helium is different than a gas of helium and argon that combine, or two different types of materials, two distinguishable types of materials. So this is very important. This whole concept is what we call the Gibbs paradox, and we will talk about this later in the course. Turns out that if we were to approach this with quantum statistical mechanics, which we do towards the second half of the course, this paradox never arises. It's just that we weren't thinking in the correct way to approach this problem. So we sort of artificially have to insert this 1 over n factorial. It will fall out naturally when we do quantum statistical mechanics. We will see many more examples of entropy and do a lot of entropy calculations throughout the course. This is just our first foray into entropy. We'll continue this later on. We're going to, in the next lecture, we're going to see how we can derive the concept of temperature from entropy. And that's a very different way of looking at temperature than you probably looked at when you were studying thermodynamics. So that's coming in our next lecture.